All right, let's jump right in. We are about to pull back the curtain on the hidden science that connects the bottle you're drinking from, the tires on your car, and, get this, even your own DNA. It's all about one amazing type of molecule, so let's get into it. So let's kick things off with a bit of a riddle. Take a look at these three things: a super tough car tire, a simple plastic water bottle, and the literal blueprint of life, DNA. I mean, on the surface, they seem completely unrelated, right? But chemically, they're all connected by one fundamental secret. Any ideas what it is? The answer? They are all made of polymers. That's it. That's the invisible thread tying them all together. And today, we're going to figure out exactly what that means and why it's one of the most important ideas in all of modern science. Okay, so first things first. Let's start by breaking down this whole world of polymers. I want you to think of them like giant structures built with tiny, tiny chemical bricks. So what is a polymer? Well, the name kind of gives it away. Poly means many. A polymer is just a huge long-chain molecule made by linking together lots and lots of small repeating units called monomers. The easiest way to think about it is like this. A single Lego brick is a monomer. When you click thousands of those bricks together to make a super long chain, you've just made a polymer. It's that simple. Now, not all polymers are created equal, especially when you turn up the heat. They basically fall into two big categories. On one side, you have thermoplastics. Think of these like a chocolate bar. You can melt it down, reshape it, let it cool, and do it all over again. And that's key because that means you can recycle them. On the other side, you've got thermosetting polymers. These are more like a cake. Once you bake it, well, that's it. You can't unbake it. If you heat it up again, it just burns. And this difference is absolutely crucial when we talk about what can and can't be recycled. But long before humans were cooking up polymers in labs, nature was already the master chemist. So let's take a look at one of its most famous creations, natural rubber. And as you'll see, it started out as a pretty sticky situation. So natural rubber is a polymer called polyisoprene, and we get it from this milky white liquid called latex from the rubber tree. Now, in that liquid, every tiny little particle of rubber is wrapped in a protein membrane that has a negative charge. This charge makes all the particles push away from each other, kind of like when you try to force the same ends of two magnets together. It's that repulsion that keeps the latex liquid and stops it from all clumping up. So how do you get a solid block of rubber from that liquid latex? Well, you have to break that force field, and this is done through a process called coagulation. You just add a weak acid, which introduces a bunch of positive ions. Those positive ions immediately cancel out the negative charge on the rubber particles, and just like that, there's nothing keeping them apart anymore. They all slam into each other, their protective shells break, and all those long polymer chains get tangled up into one big, solid, bouncy blob. But here's the thing. There was a huge problem. This raw natural rubber, it wasn't actually that useful. It was way too soft. On a hot summer day, it would get all sticky and gooey. Plus, it reacted with the oxygen in the air, which made it get brittle and fall apart over time. It was a cool natural material, for sure, but it desperately needed an upgrade. And that upgrade came in the form of a simple but totally brilliant chemical fix, a fix that launched a revolution in how we make things, the process of vulcanization. And the solution that changed everything? It was a single, common element: sulfur. That's it. Just by adding a little bit of sulfur to the mix, you could transform rubber from a sticky mess into a tough, high-performance material. This amazing process is called vulcanization, and its entire purpose is to create something called crosslinks. Basically, it's a way of chemically tying all of those long, separate polymer chains together, locking them into one single, unified network.
And the difference it makes is it's night and day. Before vulcanization, rubber is soft, weak, melts easily. After, it's harder, way stronger, much more elastic, and it can handle really high temperatures. It's also way more resistant to breaking down in the air.
So how does that even work? Well, think of the raw rubber chains like strands of cooked spaghetti on a plate. They can just slide past each other really easily. The sulfur atoms form these strong chemical bridges, the crosslinks, between those strands. So now, when you stretch the rubber, the chains can pull apart and uncoil, but those sulfur bridges stop them from sliding away permanently. And when you let go, the bridges pull everything right back to where it started. That's elasticity. Now, improving natural rubber was a huge deal, but it was really just the beginning. The real game changer came when chemists realized, hey, we don't have to rely on nature at all. We can actually design and build our very own polymers from scratch. This was the dawn of the age of synthetic. So why bother making your own? Well, to create materials with specific superpowers that even vulcanized rubber didn't have. Using byproducts from petroleum, scientists could engineer materials that were even tougher, more heat-resistant, and basically immune to chemical attacks. These were materials built for the modern world. And you know these materials, I promise, even if you don't know them by their chemical names. That strong PVC in your water pipes, the heat-resistant neoprene in a petrol hose, the super abrasion-resistant SBR that makes up your car tires, and even the incredibly stable silicone rubber that's safe enough for medical implants. They're everywhere. But, and you probably knew there was a but coming, this incredible success story has a shadow, a dark side. The very properties that make these materials so amazing have created a plastic legacy that comes with a massive unintended consequence. And this quote just hits the nail on the head. It's the central paradox of plastic. The very things that make these polymers so incredibly useful, their strength, their durability, the fact that they don't react with anything, are what make them an absolute nightmare for the environment when we're done with them. And this number really puts the scale of the problem into perspective. A single plastic bottle can take over 400 years to decompose. These materials we designed to last, well, they're lasting a little too long in our landfills and oceans. So the challenge is pretty clear. Because these materials are so unreactive, they just don't break down naturally. They just accumulate. And that leads to the massive pollution we see in our oceans and landfills. I mean, just think about it. What do we do with the millions and millions of worn-out car tires every single year? It's a huge global problem.
So what's the path forward? Well, recycling is a huge part of the answer, but it's not the whole story. The really exciting stuff is happening at the cutting edge of science, where researchers are developing a whole new generation of smart materials, polymers that are actually designed to be broken down by sunlight or by microbes, so they don't just stick around forever.
Which leaves us with this final big question. We have become absolute masters at creating materials that last. The next great challenge is to become masters at creating materials that last exactly as long as we need them to, and not a single day longer. How do we use the incredible power of polymer chemistry to design a smarter, cleaner, and more sustainable future?